Thank you. Okay, so good evening and welcome all of you to this very interesting colloquium. It's going to be given by Professor Sunil Gupta, of course, our esteemed colleague, and he is currently the DAE Raja Ramanna Fellow, both at TIFR and BRC, and of course, he was a senior professor in the Department of High Energy Physics, TIFR. It's very difficult to sort of introduce him for two reasons. One, of course, is his vast field and the expertise and knowledge and experience that ran through. In fact, you can see just a few bullet lists that is given here. But also, I mean, obviously, we know him well. I personally know him well for almost as long as I was there in the TIFR. But it is again extremely pleasant duty to formally say a few words, especially to those who there are a large number of audience on the social media. So Prof. Sunil Gupta joined TIFR way back in 1976, and as I said, he retired in 2020. He carried out research in large number of international centers, including University of Maryland, Fermilab, Los Alamos, NASA, and he also worked at CERN, Geneva, and Aachen, Germany, INFN, PISA, Osaka City University, and Chubu University, Nagoya University, Tokyo University. Some of them are the collaborators for him and his group in high energy physics and astrophysics. For the last almost 30 years, Prof. Gupta led setting up GRAPES 3 experiment at UTI, the largest astroparticle physics facility in India, and developed many new instruments and applications in not just only high energy physics, but also way beyond that, including atomic energy and other strategic applications, space sciences, and so on and so forth. And GRAPES 3 is a large collaboration with more than 30 Indian and Japanese scientists. Because Gupta was honored with obviously a lot of memberships, chairpersonships, professorships, and many other national and international awards by bodies, including Astronomical Society of India, International Astronomical Union, Paris, National Academy of Sciences of India, Allahabad, and Commission C4 on astroparticle physics of IUPAP, to which he was also a past chair. International Emulsion Chamber Committee, VIIT Pune, Chibu University, Japan, and the list goes on. And recently, as many of you would have come to know, he was awarded the prestigious O'Kelly Medal in recognition of his significant contributions to the field of astroparticle physics for an extended career and for his leadership of the GRAPES 3 experiment at the Cosmic Ray Laboratory in UTI. I mean, on my personal front, I can add a few lines. I mean, he has been a person who was always, who spoke or who speaks the language of engineers, language of instrumentalists. So it was much easier when we talked to him. He used to understand what is the real backbone of any physics experiment, and more so in the large-scale high-energy physics experiment. And I think one of the testimony to that philosophy in some sense is the kind of results that he and his colleagues presented here the last few years, which actually sets not just building the instrument, not just setting up electronics, but running it to a level where to the precision, to the stability, so that the data quality that you actually look at and able to present really shows that how well you are not only design an experiment but operate it, keeping it such a high level of let us say stability. So I'm sure some of those aspects maybe as a passing or as a kind of topics he might deal with, but that is something which we all love and which we all like him in as an experimentalist. So we expect to see listen all to this. The title says Journey of an Experimental Cosmic Ray Physicist. So over to Professor Gupta.
Thanks, Satya. Thanks to all of you for coming here, and to my colleagues who have joined from India and Japan. Indeed, it is always a pleasure and an honor to speak in this lecture theater. It is a very historical venue. So, as the title suggests, I'm going to tell you about my journey as an experimental cosmic ray physicist, which, to say the least, has been the most unusual one, as you would see. I'm not going to talk about too many technical things. I'll touch upon different aspects of it. So I've labeled basically 5 phases. The first one is setting up and getting results from a Cherenkov experiment at CRL-UT. This phase lasted about 7 years, which culminated in finally me writing my thesis and getting on with life. Second was Graves 2 EAS array, again in CRL-UT. This was the phase during 1986 to 93. You can see it's not in chronological order. That is because I took 2 breaks. First one was to visit Fermilab to work on a very elegantly named experiment E557/672, which doesn't convey anything. It is near Chicago from 1983 to 86. And then I had another stint at NASA Goddard Space Flight Center working on ISOMAX experiment, which is a magnetic spectrometer. This lasted about 2 years, 96 to 98. And but mostly I have been working for close to 30 years on the Graves 3 experiment. Now, oops, it's okay, I can, it's locked. Huh?
Maybe it is not
Oh,
on.
is it here?
No, it is on. It is on.
No?
Yeah. I think we need to click on this. Yeah.
Oh, okay, okay. Okay. So, okay, good. Okay, so before I begin, I should pay tributes to our founder of this laboratory, Professor B.V. Srikantan, who has been a real inspirational figure in my life. I place him, alongside my parents in terms of influence he had in my life. This young Professor Srikantan, this laboratory he set up, founded at the instance of Dr. Bhabha in 1955 in Ooty, the same year I was born. This is Professor Srikantan visiting Ooty in 1982. This is during his visit in 2001, which coincided with the visit of Professor Jha, the then director. And this was his last visit to Ooty in 2016. This is son Ramesh, and these 2 ladies are the caretakers of guest house. And as always, Professor Srikantan was very gracious. My last visit and last meeting with him was in 2018 when I visited him in Bangalore, and he insisted that I stay in his house. And he was a remarkably independent person. This is Professor Srikantan making his evening coffee. He never liked anybody doing anything for him. This was always a lesson for all of us. Okay, and this picture is another historical picture. This is Professor S. Miyake, Professor Saburo Miyake, who initiated the India-Japan collaboration way back in 1960, early 1960. But this picture was taken in 1967. You can see a very young Professor Kawakami, who was, I think, a graduate student at that time. This Professor Kawakami today, he has been an integral part of this collaboration from the beginning till now, and has played a really seminal role in building up this India-Japan collaboration. And I think I can't think of any other figure having such a massive influence. This picture I put for a funny reason. See, soon after I joined, I went to Ooty in September. In December, a new Jeep arrived in Ooty for use of laboratory members. And then it was discovered there was no driver. So Professor Srikantan asked, does anybody know how to drive? And I'm the one who raised hand, because though I was 22, but I had already 10 years of experience driving. So I was put through a driving test and was duly authorized to drive. And I had the unique distinction of, chauffeuring every director of TIFR from M.G. Menon, B.B. Srikantan, Viren Singh, Jha, Bhattacharya, Burma, Sampath Kumaran Trivedi, and Ramakrishnan, except for last one. By that time, I had retired. And of course, I never met Dr. Homi Bhabha. So I don't think this is a record many can match. And that made me feel very close to the drivers of TIFR, because we share so many common things. Okay. This is a picture. This is me in sometime in the early 1980s. And we set up this atmospheric Cherenkov array in the backyard of Cosmic Ray Laboratory. This was in 1978. Actually, the instrument was set up in 1976. This was expanded. 20 reflectors are there. 8 are large area. So my first task as a physicist was to work on this gearbox system. This is a 3-foot diameter mirror, 90 centimeter. And it had a, axis which is parallel to Earth's rotation axis. And this is called right ascension gearbox, which is to steer it in east-west direction. And there is another one called declination, which you can barely see in this area, which is to orient it in north-south direction. So we had to balance this system so that, you just have to turn the stepper motor to track a source. And when we implemented this gearbox for these large mirrors, we found that either it was going too slow or too fast. It was not tracking as we expected. And we struggled and scratched our head for almost a month, but couldn't figure it out. Until one day it occurred to me that if you turn this mirror around, and this was a particularly heavy one, the mass distribution changes. And if the mass distribution changes, it is no longer balanced system around that axis, and it exerts a torque. And because of that torque, this shaft, which was only 2.5 centimeter steel rod, was getting twisted. So, of course, once we figured out, it was very easy. We increased the diameter to 4.5 centimeter and the problem got solved. Because these were the days when we used to use protractor to measure the angle, not fancy shaft encoders. So it was quite an exciting adventure. Here is my thesis supervisor, Professor Ramanna, who was a really dominating figure. Those of you who have heard of him or have met him would know. Satya certainly knows him. He was not referred to as Professor Ramanna. He was always referred to as Khuda, because he always had the last word. Okay. And here he is talking to Prince Philip, husband of Queen Elizabeth II, who died recently. And this is young Professor Arnold Wolfendale, and then became Sir Arnold Wolfendale. He's holding his own. And it was just a sheer coincidence that Professor Wolfendale passed away at the age of 93 in December 2020. Professor Ramanna a month later in January 2021. And Duke of Edinburgh in April 2021 at the age of almost 100. Okay. And I had the honor of paying tributes to Professor Wolfendale and Ramanna as chair of the C4 during the ICRC, which was held in 2021. Okay, so once we did this experiment 4 years, we found the light condition became very bad. Uti was developing and there were too many lights. You could not make Cherenkov observations, which required dark nights. So Professor Ramanna told me, okay, we have to go elsewhere. Where do we go? We go to Radio Astronomy Center, which was 10 kilometers away in wilderness. There were no street lights, city lights there. So the place looked almost as it does now. This is a picture 40 years later. And this is Ramesh, who is taking a picture of this building while he's being photographed. And so all these bushes were there, and the location, this is the radio telescope, and this is about 250 meters east of radio telescope. So he said, we have to go. Then I said, but what do I do there? He said, well, we are going to construct a laboratory building. I said, I don't know any, I don't have any civil engineering experience. He said, oh, don't worry about it. You work with the DAE civil engineer and civil supervisor. They'll do all the work. You just hang in there, make sure that things happen. Okay. Of course, I had no clue. I immediately agreed. And then later on, I discovered that the civil engineer will come once in a month or once in 2 months and spend 2 hours and disappear. The civil supervisor will come once or twice a week for an hour and disappear. So I became de facto the civil supervisor or civil engineer. Anyway, I spent some time figuring out how to, mix cement and sand and different ratios, concrete, etc., what the strengths are of different category of concrete, how to have structures, how to align them, etc. But the first job was to clear these bushes. And there were no tools like, excavators, etc. available. So you had to do it by hand. So we hired 8 to 10 laborers. Now those laborers were living in town, Uti town, which was 10 kilometers from this site. So my driving skills came in very handy. So I used to go out in the market, have them put in the Jeep, pack it, and then drive to the site, and they will work. And then I found things were going very slow. All they had was fork, spade and axe, etc., to cut these bushes. And they look very, harmless, but they're actually very thorny bushes. So we had to get gloves, etc. Then I decided, okay, I should also do some work with them. And then suddenly things speeded up. So I learned how to cut bushes and, do that kind of stuff. And things went along. So we cleared area of almost equivalent to 1.5 hectares or about 4 acres. And this was the building which was constructed. This picture was taken recently by Hari and Ramesh. You see, these are 4 bunk beds. So, sometimes it will get cloudy or rain. You can't have any observations. So we had bunk beds. Each bunk bed is about 6.5 feet by 3, little over 3 feet. So it's very comfortable size of a first class berth. And there are 4 of them. And there's a bathroom. The door has been removed. A lot of junk has been dumped. And this is the side where the control room was there. You can see these conduit pipes are running to bring power. And this is the entry door. So I was very happy. This is the bus bar where the electrical distributions were there. What I was happy to learn from my colleagues that still there is no lag, no leakages, no major cracks. And this building, which was built in 1980, still stands. Actually, with some sprucing up, it can be used again. So I feel pretty good about it. And this was the configuration of those mirrors. So the cluster of 8 was put in the center, and this is not to the scale. The ring of 10 mirrors were put at a radius of 55 meters to measure the arrival time of Cherenkov photons so that we can get a better measurement of the arrival direction. And this, of course, all this work constituted my thesis, which was submitted in 1983. And then, you know, subsequently, BRC group also got into this field. And now they have built this big maze telescope. And recently, I was invited to BRC as part of the review committee of Astrophysics and Space Sciences Division. So the person who heads the division told me my thesis is still being used as a reference. I feel very good about it. Whatever effort I put in building these buildings and cutting pushes has not gone, you know, to waste. This was, then I moved to, on sabbatical to Fermilab, and I worked on a high energy physics experiment. These were the early QCD days. QCD was not yet established as a theory. So we were studying high PT jet production in proton nucleus collisions at 800 GeV. This was called Tevatron, but it had not yet reached the energy of 1000 GeV or 1 TeV. It was operating at 800 GeV. So my responsibility was to build this hadron calorimeter with which had layers of scintillators and iron plates, and they were read out by these wavelength shifting rods. So this was a very good experience. And when I was doing that, one senior scientist came and told me, oh, well, since you are there all the time in Fermilab, though I was working at University of Maryland, how about you take care of the beam line? So I had no clue how to run a beam line. He said, oh, it's not a problem. It's only 1 kilometer long, or maybe a little more than 1 kilometer long. And it has only, a couple of hundred magnets. And only 10% of them are superconducting magnets. I had never used either a conventional or superconducting magnet, unlike those of you who work with pelletron and low temperature physics. I had no clue. But he was a very good person. So he said, you don't have to do much. You see, you just watch the beam counters. If the beam shifts to the left or right, you have to change the current. The specifications are given here. Bring the beam to the center. And if it spreads out, you control the quadrupole magnets. It will focus the beam, and that's it. So I said, okay, all right, this I can do. Oh, by the way, you have to also take care of the Cherenkov counter, which is 300 meters long. It's filled with helium gas because we are trying to measure very high beta particles. Okay, so that was additional responsibility. But then I found it was not all that complicated. It looked very massive job, but it was not so difficult. Okay. So this was my second stint outside, and that time I worked on an experiment called ISOMAX, basically to measure using it refers to isotopic measurements using a magnetic spectrometer. It had an air core magnet which went up to a field of 1.6 Tesla. So there's no return yoke, so the field spreads out. So one of my jobs was to calculate the value of magnetic field at every spot, which what I did was I just went from first principles. So I could do a very good job of calculating, which agreed with whatever measurements were actually made. And this is the team that we worked on. This is our group leader, Bob Streetmatter. Unfortunately, he also passed away a few years back. And this guy is John Mitchell. He's a very accomplished, I have never met a more accomplished person. He had a degree in mathematics, master's. Then he did PhD in low temperature physics and decided to move to cosmic ray physics. He was an exceptional guy. So he will not let anybody touch anything here because he didn't trust anybody. So one day Bob Streetmatter called me and congratulated me. I said, for what? He said, you are the first guy he's allowing to operate the magnets. So congratulations. So anyway, so that was a fun time. And then we went to Canada, to Lynn Lake, place in Manitoba, to launch this is the payload, which I showed you in the previous thing. And this is, of course, a very typical thing. Only thing in US, they use not hydrogen gas like we do, but they use helium. So this is the balloon, which is total volume is 1.1 million cubic meters. Now, it's very hard to imagine what is 1.1 million cubic meter. So you can think of, you take all the buildings that are there in Nariman Point, you can fit inside when it is fully inflated. And it goes up to an altitude of about 40 kilometers. And then here it is being launched. This is the parachute, which will be cut, once it is cut, the parachute will open. And this is after the flight ended, after about 20 hours, the instrument landed. And we got some interesting results. And then 2 years later, they upgraded and they flew again. Unfortunately, the end was somewhat ignominious. It crashed. So when I met my colleagues, I said, see, this is what happens when I'm not there. Anyway, so back to Cosmic Ray Laboratory. This, of course, is a more recent picture, only 7-year-old picture. This is the entry to the Cosmic Ray Laboratory. Okay, these are all ancient buildings. They were constructed in early 20th century. So more than 115, 20-year-old. So this time we worked on setting up a water Cherenkov muon detector. And this was completed. We started in 86 and we started operating in 1990. What you see inside is a tunnel. It's a concrete structure. It's 1 meter high, 70 centimeter wide, and 21 meter deep. And what you see at the bottom are two 20 centimeter high water tanks, which are filled with pure distilled water with something else mixed into it. And here are photomultipliers to collect signal. Now, when we did the testing, and I worked with Srivatsan, who was one of the PhD students, whom some of you know. So Srivatsan, I think you know him, right, Lokesh? You know Srivatsan very well. So Srivatsan worked on it, and we found that minimum thickness we need is 60 centimeter water column to detect muons with efficiency of more than 95%. If you put 60 centimeter high water tank, only 40 centimeters is left. No servicing of any instrument is possible, right? No human being can go inside. And we didn't have automated equipment, and you can't move each tank weighs after it's filled with water more than 200 kg. These are aluminum tanks. So we came to know that there is a wavelength shifting dye called beta-methyl-umbelliferon, which dissolves in water in presence of alkaline solution. But we can't use alkaline solution because we are using aluminum tanks. So we experimented. We said, let's try if we can dissolve it. And we found we could dissolve up to a concentration of 2 milligrams per liter. And that did the job. The light yield went up by a factor of 3, and we could reduce the height by a factor of 3 to 20 centimeter. And these railings are to put a trolley on it. Some of those of you who have been there in Ooty, you put a trolley, you lie flat on it and propel yourself by grabbing the railing. And I was one of the first persons who offered, because I realized after my experience of setting up the array that unless you take the lead, nobody will take you seriously. And I can assure you, even today, I can go inside. Even at this age, no problem. That confidence I have. Anyway, so like this, there are 16 tunnels. Each tunnel houses 12 detectors. Each has an area little over a meter square. 16 times 12 is 192. This is the entrance to those 16 tunnels. You get 192 tanks. Total area rounded off is about 200 meters square. The threshold of 1 GeV, which is produced by putting 10 feet or 3 meters of soil above this. This has been running since 1990. And Srivatsan did, his thesis was on this, and some other work has been done. Okay, now this is the view from the present guest house of looking at Grapes 2. You can see all these scintillator detectors. There are about 85 of them. And this flat area is the top of the muon detector, where you have this 3 meter soil dumped on it. To prevent landslide, because Ooty is known for landslides, we had put sandbags on this side. Other side, we had built a retaining wall because building is there. Again, it has withstood the test of time of over 3 decades. So I think we are done okay. Now, this picture is very important. You see, I cannot fail to mention the name of these two individuals, these two remarkable individuals. This is Mr. Bellam Srinivasa Rao, who by training was a civil engineer, but in my opinion, he was an exceptional, not just a civil engineer, but also a mechanical and electrical engineer, though he didn't have any formal training in that. Every single structure you see in this picture, or for that matter, which was built by members of this collaboration, has been constructed by Mr. Rao. This experiment would not have happened without his contribution. And the kind of quality of work, the kind of work he has done is just mind-blowing. The second is Mr. Ismail Muhammad Harun. He was formerly he was gardener, but I consider him to be either a botanist or a horticulturalist. He knows the flora and fauna of Nilgiris like nobody else. And so apart from landscaping, beautifying the campus, and you saw examples of that in the earlier picture, it's all handiwork of Mr. Harun. And he retired just a few months before I did. And in addition to his work, he used to participate in annual flower show and compete against people who came from corporate sector and other public sector undertakings and beat them hollow. This is his haul of cups he won over a career of 25 years. There are more than, I think, 215 or 16 first prizes. If he got second prize, he felt humiliated. How can I get... See, we fed cricketers if they score 48 or 49 centuries. He is a guy who has hit more than 200. But anyway, so these two people made Grapes 3 experiment what it is. Okay, this is the view of the present-day Grapes 3 experiment. These are the scintillator detector. This is the 4 muon telescope, which was primarily the responsibility. The detector part was the responsibility of our Japanese colleagues, led by Professor, earlier Professor Ito was there, then he retired, then mainly Professor Kawakami and Professor Hayashi, and their students. I see Professor Oshima is there, Tanaka is there. Many of them have done their PhD and they have contributed to it. But what I want to draw your attention to, except for this Tata bus, everything else was made by the members of the laboratory, not by outside contractors, not by outside firms. It was all done by the... So this is, as Satya mentioned, there are about, this is, of course, I'm referring to 2020. There are more people have joined since. We have groups from India and Japan. And this collaboration is going strong. This probably, in history of science, may be one of the longest collaborations, over 60 years. And we have developed a bunch of things: plastic scintillators, proportional counters, signal processing, electronics, data acquisition system, computer clusters, not in few, but in thousands. Okay, this is, since there are a lot of youngsters, this is a Google view of the experimental site. This is the new muon station coming up. This is the existing 4 super modules, and these dots you see are 1 meter square scintillator detectors. This is a picture taken sometime in '96. This is young Srinivasa Rao. And we wanted to have our laboratory building top look like a Japanese pagoda. We didn't quite get that right. So this cone has been put as part of that structure. And you can see the muon telescope are under construction behind it. Okay, so this I wanted to show you. This I have shown many times, so some of you will remember. These scintillators are 1 meter long in this direction, 70 centimeter wide, and 4 centimeter thick. And if I put a newspaper at one end, you can read it from the other side. That's how good the transparency is. You can take the best quality glass, the one like here, you cannot see even 10 centimeter. So it has very little attenuation. It's very high transmission. It has large light output. So this actually we built for BARC, for the reactor projects group. And I think this particular radiation monitor we made earned us more credit with Department of Atomic Energy than anything else we might have done. And they greatly appreciated this contribution because it served a very important strategic gap in their program.
What do we actually, what is the composition of it?
You mean the plastic scintillator? Okay. See, that is a long story. I can tell you afterwards because it will take me an hour. We spent 3 years using raw materials. Raw materials, of course, we didn't make. We bought it. But to turn into a sheet of plastic which has all these qualities, free of bubbles, free of some kind of color layers, etc., it took us 3 years. Once having done that, it's a casting process. And once having done that, now we can create any shape or size we want. So we made explicitly for BARC. And we had done for not just BARC, for many other groups. Okay. In fact, I have had the privilege of visiting most of the DAE centers because all of them have these requirements and they would like to utilize because something which is there, and I will be very happy if it is used not just by TIFR, but by other groups. So we have helped many other groups to set up these kind of detectors, and we'd like it to spread further. Now, I said that it is, all the good properties about it. So I want to give you an example. So this is, you see, this blue is when rain comes. So this is rains. This is time. This is sometime in 2007, time of the day in Indian Standard Time, and rain in millimeter of rains millimeter per minute. That is what is plotted on the secondary y-axis. On the primary y-axis, the rate of a scintillator detector. By the way, this is not the actual scintillator detector which we are using. It is a special scintillator detector with high sensitivity we made. But you see, whenever rain comes, the counting rate goes up by 200%. In reality, the count rate goes up only by 2%. But our detectors are so stable that 2% is very, very significant, because generally rates don't fluctuate. So where does this increase comes from? What has radioactivity? And that, of course, I think most of... Okay, so green line, so there were two detectors. So, I should explain. See, there were two scintillators which had specially sensitive, which were especially made sensitive for low energy gamma ray detection. Okay. And what we did was we had a funnel to collect the rainwater, and it was dropped on a container on top of this scintillator detector. So when this first rainfall came, the water was put on top of what was labeled as red. The second so in first rainfall, you see very modest increase, right? And in the second case, the water went into this over the second detector. So all the radiation which is present in fresh rainwater is guided to the second detector. So that's why in second case, you get an increase in green, which is shown in green, that is the second detector. Red is the first detector. So there are two detectors. Just to cross check that, we are not seeing anything unusual. And you can see here, rainfall was much higher than there. So the peak is also much higher here than there. So, okay, again, this could be a topic of a colloquium. I don't want to get into that. So we did, of course, afterwards, once we understood what it is. And in fact, Pranava was involved in this analysis. So what we did was we collected fresh rainwater and used a sodium iodide detector. I see Indranil is there. So Indranil had provided some sodium iodide detector. We used that to measure the energy of gamma ray lines. And we could see there gamma ray lines between 300 keV and about 2.2 MeV. And then, of course, it's very easy to figure out because we know the decay time. So these are produced by decay of radon, which is, of course, comes out of Earth's crust, which goes into lead-214, which has a half-life of about 27 minutes. And then it goes into bismuth-214, which decays with a half-life of 20 minutes. So the combination of these two appears as if it is a decay time of about an hour, decay life of about an hour. So this is basically, but if you ask the question, how many radioactive nuclei are there that you are detecting, it's typically 1 part in 10⁻²1. So it's a very sensitive in terms of picking up this kind of radiation because background is very, very small. Okay, now this is the tale of when we built the new muon telescope. For that, now when KGF lab shut down, they had almost 8,000 proportional counters. They were in various stages of disarray, or let us say disuse. So some of them were in very bad shape, some of them were in okay shape. So the ones which were in okay shape or in a functioning condition, we used in making the existing muon telescope. There are 4,000 of them, which were just bad. They were not working. So we didn't know. So our friend Srinivasa Rao decided he believes in never throwing anything away. So he constructed a shed and stored them and made sure that no water goes there, no rusting takes place. So after they were brought there in 1909 or so, in 2018, 2017, we decided to construct the new muon telescope. Now, these are very specialized single seam welded tubes, which were actually imported from Japan. And we tried Indian tubes, but they had many problems. And importing them would have cost us a fortune. So we decided to recycle them. So here is my colleague Paul Francis and his help, who are cutting this tube to right size. Here is the crew led by same Mohammad Harun Gardner, cleaning with water jet, then if require abrasive powder, and then drying with compressed air. And then these two are expert welders who actually by training are carpenters. So Rao said, so we first tried, we said, let's do it professionally. We went to L&T and they had some expert welders who did welding for us. And we found success rate was 65%, which was clearly unacceptable. That means 1/3 of the counters we had to throw away, which we didn't have the luxury of. So Rao said, look, I know what these guys are doing. Give me time, couple of months, I will train my people. So these two carpenters were trained in TIG welding, tungsten inert gas welding. And after a few trials, they achieved a success rate of higher than 99%. Okay, this was a figure. I think Hayashi-san is there in the audience. He can confirm. This was the figure given by Hayashi-san, who's a very conservative person. He said, I cannot be more accurate because we have made only 4,000 counters. So you cannot have an error, better than 1%. So that's how he said it's more than 99%. And I had challenged Rao that you should at least be able to deliver 10 counters per day, so that in a year we can make 3,000, or in a year and a half we can make all 4,000. So whenever I gave a challenge to Rao, the response was characteristic. He started with 10 and then he went up to 30 counters per day. And then poor Hayashi-san came to him and said, please slow down, because we cannot maintain the downstream production at that level. Because this requires further work. And that further work involves brazing a hermetic seal on both ends so that you can thread the 0.1 millimeter tungsten wire and a needle valve for evacuation and filling of gases, and then testing. So that I will describe in the next slide. So here's Manjunath, who is testing a stack of 10 proportional counters in parallel. This entire operation was supervised by Hayashi-san. He came on 2 occasions. Of course, work was carried out by our colleagues, but he's the one who was making sure that there are no compromises anywhere. Every parameter matches our goals. So it tests for leaks, and if any leak is there, you set it aside. But you see, if you get a leak, fixing that is a huge challenge. So that is why 99% success rate was very important. And then after we had tested it for 48 hours, there are no leaks. The whatever outgassing is within permissible limits. Then it is put in a stack. There are 16 counters parallel to each other and 8 layers. And then you have front-end electronics to process the signal. And of course, once the counter is certified, it is coated with zinc chromate and then white paint is applied. This is the finished one. Now here the challenge came, because the front-end electronics which we are using was earlier designed by our Japanese colleagues and I think built in KGF. It had some issues. So we gave this, I asked Ramesh, who is a brilliant engineer, who is also, I believe, in the audience, to design new front-end electronics. So first, let me tell you what we are seeing here. This is the signal due to muons going through proportional counter. And it has a typical shape which goes by the name of Landau distribution, because it was first calculated by Lev Landau, a great Russian scientist. And then you see 2 small peaks. And these peaks are labeled iron and zinc. And that is because these tubes are made of iron and it's coated with a layer of zinc to prevent rusting. So what happens is, occasionally a muon knocks out an electron from the innermost shell and an electron from a higher shell jumps. And that produces a characteristic 6.4 keV X-ray line. And that shows up as a line here. And in case of zinc, which is slightly heavier metal, it is 8.6 keV. So these two give us the energy scale. If it's 6.4, this 8.6, you can calculate it's about 20 keV. And that's exactly what we expect from Monte Carlo simulations also. Now, what is remarkable is, if there is no noise in the system, you should get a flat background. Again, if you want, I can discuss with you in detail why it should be a flat background. And that is what we get. We were all surprised to see this flat background. None more than me, Hayashi-san and Kawakami-san, because earlier the background used to exponentially go up. So we had a problem of noise. Now that has disappeared. So, and Ramesh made not 1, 2, or 3. He made, in fact, he was involved. Wiring was done by our colleagues in Grapes Tea. And Ramesh was involved in testing and making sure all these things are there. and he successfully delivered 8,000 channels. 4,000 of them are already operational in existing muon telescope. This is where the construction of the new muon telescope is happening. You can see there's a concrete platform. There's a layer of proportional counter. We can't see. I'll show you later on. Then there is a layer of concrete, 15 centimeter thick, a slab. This, of course, is all Rao's job. Then second layer, perpendicular. Then third layer of concrete. Then third layer of proportional counter in parallel direction. And finally, one more in perpendicular. And then what do? You close the entire thing by putting a roof. And then, of course, pandemic struck soon after and everything stopped. And this work was completed in last summer. Of course, still a lot of things have to be done. If you look at this area, you can see people walking around. This is actually slightly larger than Homi Bhabha Auditorium. So it's a really huge area structure, but it is much better designed. You can walk through passages. It is, it is much easier to work with. Anyway, so much for the construction. Now let me come to some of the results and some of the people. So this is, so to summarize, we have approximately 400 plastic scintillator detectors, one muon telescope of area 560 square meter square, and it allows us for several high precision measurement. And here is a list of people who have done their PhD in red, who have already completed. And the purple ones are the ones who are doing it. There, I must have missed a lot of names. This is somewhat older information. Okay, so the objective is, of course, to study cosmic rays. And the main thing about cosmic rays is that they are the highest energy particles in the universe. And one would like to understand where they come from, how do they get accelerated to such high energies. So I have listed 4 astrophysical settings. The first one is actually on Earth, acceleration in atmospheric electric field, where you can experience acceleration as high as a GeV. Second is our solar system, where energy scale goes up by a factor of 10, and so does the size of the accelerator. And finally, galaxy itself serves as an accelerator of cosmic rays. And there the energies are almost 100,000 times higher, about a peta-electron volt. And finally, one could look for multi-TV diffuse gamma rays. This is something which we haven't really paid much attention to, but there is a potential to do that. Ramiz, who is also in the audience, is planning to do some of this stuff. Okay, so what I want to tell you is, it is possibly the most sensitive muon telescope. I think as of now, it is the most sensitive muon telescope, and I will tell you why it is most sensitive. So not just because area, there are muon detectors which are much larger area than this, 10 times larger than this, but they don't have capability to measure direction. So what you have is, you see layers of proportional counter, one layer in this direction, the second in perpendicular direction, in between this concrete. So there are 4 layers. Now, if you see a muon goes through all 4 layers, let's say it hits this counter, which is counter number 21. It has a dimension of only 10 centimeter in this direction, right? Where I'm moving this pointer. So you know it's positioned to an accuracy of plus minus 5 centimeter, but you don't know in the perpendicular direction because it's 6 meters long. So you go to lower layer, then you will get, so let's call it Y coordinate. So you get one Y and one X. You get second X and second Y. So think of a graph paper, 2 graph papers, which are separated from each other. So if you have one X, one Y measurement on the lower graph paper, and you have one second X and second Y measurement on the upper graph paper, you join the 2 points, you get the direction. That's basically it. There is no fancy science involved in it. Very straightforward geometric reconstruction. This is shown schematically. Of course, there is a difference, not a graph paper, but we do it in 2 independent projection planes. But you can combine that information to get the absolute direction. So what we do is we take the proportional counters which are above and below each other, that we call vertical direction, and then we take 6 on either side. So we get 13 direction in one projection plane and 13 in the perpendicular. So basically we divide the field of view into 169 pixels, or 169 directions. It spans an area, a solid angle of 2.3 steradian. So now this is where the punchline comes. Everybody else has a muon detector, which means they have only single pixel. We have 169 pixels. So it's far superior to any other instrument. It can do things which no other instrument can do, at least as of now. Now I want to tell you why it is such a precise instrument. Okay. Here are some actually plots from data. Now, I have to take liberty in terms of simplifying things because of lack of time. See, as I stand in front of you, the atmospheric pressure near my chin is higher than near the top of my head by only about 20 micron of mercury. It's a very small difference, but there is a difference. If I raise the height of this muon telescope by 20 centimeter, it will find that the muon intensity has changed. So its accuracy in terms of measuring atmospheric pressure is equivalent to 20 centimeter air column. It's also, the muon intensity that we measure is also sensitive to atmospheric temperature, not temperature here, but upper atmosphere where the muons are produced. In Ooty, the atmospheric temperature changes by plus or minus 1 degree Celsius or 1 Kelvin in a year. So in summer, it's 1 degree hotter. In northern hemisphere, it is in June. And in winter, it's 1 degree cooler, plus minus 1 degree. But you see how much effect it produces in terms of muon intensity. We can measure the temperature to a precision of 0.06 degrees. So it's a very sensitive probe of temperature of the atmosphere. It's also very sensitive to what happens in space. Though I'm not going to talk about it today, but we can do space weather studies because you see in this light blue color is the magnetic field measured at L1. Now, you all have heard of Aditya L1. Okay, this data predates Aditya L1 by 22 years. So these magnetic field measurements are provided by an American NASA satellite. So they give you measurement in nanotesla. Now, it's very easy to understand. Earth's magnetic field is about million nanotesla, okay, to put context. So the interplanetary magnetic field goes on varying depending on the condition of space. If there is some activity, the magnetic field increases, otherwise it decreases. And if you see cosmic ray muon intensity, that is also following the same pattern. That means whatever happens in space affects what happens on ground. How it happens is a matter of debate, and that is actually is precisely the tool we use to try to understand what is happening in space. And what is our sensitivity? We can detect muon intensity changes as small as, actually 0.1% is a conservative number. We can do much better than that, which corresponds to a magnetic field change of 0.1 nanotesla, which is the sensitivity with which all the space probes can measure magnetic field. They cannot do better than this. So this instrument is actually as sensitive, if not more sensitive. So I showed you it's a good barometer, thermometer, interplanetary magnetic field. For measuring it, it's a great magnetometer. Next, I'll show you, it's also a good atmospheric voltmeter. And it's also a great ammeter. It can measure currents as small as 1 femtoampere. For people like Lokesh, or our colleagues in condensed matter physics, who always talk of femtoampere, so I thought it's good to quote this number, with a precision of 1 attoampere, which corresponds to flow of only 6 muons per second. So now I want to give you an example of application of all these things, which I'm not going to give you too many results, only one result. Now, why I have chosen is, there is a good reason. This is the last important result we got. And second thing, it's also something everybody understands. There's good reason to study thunderstorms because they are the leading cause of death by natural phenomena across the globe. For example, in our country, nearly 2,000 people die every year. These are recorded deaths. Real death number may be much higher, we don't know. And worldwide, several tens of thousands of lives are lost, okay, every year due to thunderstorm or lightning strikes. Here I have put 2 news items, both from BBC. 3 dead after lightning strike near White House. So people in White House are also not secure, right, from lightning threats. Bihar lightning strike kills 20 in Indian state. This happened within 1 month of each other. So, see, once lightning strikes, there is no protection possible. But its surprising thing is very little is understood about thunderstorms. The first authoritative study was done by great Benjamin Franklin. We all know, we have all read in our school books that he was flying a kite with a key bunch hanging. When a thunderstorm passed, it caused sparking and all that. But that's a popular story. In reality, he did very serious studies. Although he was a self-taught man, but a remarkable individual. And he used to, you see, when he did these studies, USA was not an advanced country. It was an impoverished agricultural economy. So he used to do research, make his measurements, and communicate to a gentleman by name Mr. Collinson, who was FRS in London. Because you see, so what Mr. Collinson did, he collected all the work of Benjamin Franklin and published as a book with title Experiments and Observations on Electricity made at Philadelphia in America. See, it says America, it doesn't say United States of America, because there's no United States of America. This was published in 1751. United States declared its independence in 1776. So this predates by a quarter of a century. Okay, so there is a, okay. Anyway, I don't want to, this letter is an amazing piece of correspondence by Benjamin Franklin. He's the guy who gave the idea of, there are two types of charges, positive and negative. Before that, people didn't know that. Second thing, he was the guy who invented lightning arrestor, which is used even till today. Okay. And because of that, in addition to that, he was the person who is considered the founding father of United States of America. Because the people like Washington and Jefferson and all the other great presidents of USA, they were all fighting each other busy, and they were not able to agree even on what constitution to have, what kind of, united union to create. So it was Franklin whose intellect and respect that he enjoyed, that he could do it. So they wanted him to become the first president, but he refused because he was past 70 years old, which was considered really old in those days. But because he's a founding father, his portrait appears on the highest denomination dollar bill, that is $100, just as we do. We put Mahatma Gandhi in our 100 rupee and all other denominations. Okay, so for next 150 years, there was not much progress until these two gentlemen, Elster and Geitel, two German school teachers who actually were outstanding scientists, but decided to teach in high school, which is in Germany called Gymnasium. So they were teaching there. And one was very good in theory, one was great in experiments, and they were childhood friends from kindergarten till their final degree from, I think, Göttingen. They were together. And they were the first one to show that it is thermal draft of moist air. When it goes up, the air cools down, and water, moisture condenses into water droplet. It continues to rise. Eventually, it turns into ice crystals. And at some point, the draft stops, updraft. The ice crystals start to fall. They have a tendency to stick together, grow into larger in size. And when they collide with upgoing water drops, charge exchange takes place. So positive charge goes up, negative charge comes down. So this mechanism was proposed by them. And not much happened thereafter. Until 1929, 30 years later, a great scientist by name C.T.R. Wilson, who was the inventor of cloud chamber, for which he could receive Nobel Prize in 1927, he basically estimated, not measured, that the electric field inside a thunderstorm is 5 kilovolt per centimeter. And he estimated the size of the cloud is about 2 kilometers, so the total voltage should be about 1 gigavolt. And he published this thing. And since that time, people have been trying to measure the voltage. The maximum voltage they could measure was about 7 or 8 times smaller. And so conventional wisdom is that voltage higher than that cannot exist. And we came to know that. Why I'm saying it is because we experienced that afterwards. Now, this is the field of view of Graves 3 muon telescope. Now, in 2011, again, at the insistence of Kawakami-san, we installed 4 electric field monitors, which are separated by 6 kilometers. This is Raj Bhavan, and this is Graves 3, and 2 in between. And then we used to have, weekly meetings, and, Pranaba and other colleagues will report that we have thunderstorm activity, and we saw this. And we kept on doing it for years together. Then until once it happened, then I started thinking, okay, fine, we see all this. Can we make use of it? Then it occurred that we are detecting muons which have energies of GeV, giga electron volt. So if you are able to modify their intensity, that means the object that is causing the change in the intensity has to have voltage comparable to gigavolt. Otherwise, it's not possible. So this was an event. Now I'm again cutting long story short. This is the intensity of muons as a function of time every minute. And you see it's fluctuating, and this is 1 sigma error. It is consistent with statistical fluctuation. Suddenly at this time, 10:42, it drops, And for 18 minutes, it stays low. And this is a 20 sigma effect. And as you all know, that is impossible to explain. And when we look in the field of view of muon telescope, you find all the this effect deficit is caused on the eastern directions, not in elsewhere. Green means no change, blue means deficit, up to 2%. So now, here is a model to explain this. Think of muons, which are charged particles, predominantly positive charged particles going downwards. It's like muons are same as electrons, except they're 200 times heavier and they're radioactive. So as they are going down, they constitute a downward flowing current. So you can think that it's powered by a battery, let's call it muon battery of potential E1. And then it encounters thunderstorm, which is top is positively charged. So it will oppose the flow of this current. Let's state that its potential is E2. So the current before the thunderstorm is I1, which is given by this equation, where R1 plus R2 is the resistance. And I2 is E1 minus E2 divided by R1 plus R2. If you take the difference, you get delta I, which is nothing but E2 divided by R1 plus R2, or E2 is equal to change in current multiplied by resistance. So now we know the change in current, this is what we are measuring. If only we could measure R1 plus R2, we'll know what the voltage is. Now that's easily said than done. So this required a huge calculational effort, because first of all, muons are not powered by a battery. They are high energy particles. They're radioactive, they decay, and sometimes you produce more muons in cosmic ray interactions. So all that, so we had to do detailed simulation. This work was done by Hariharan. And what he showed that, so this is current, change in current as a function of voltage. So if you apply 0 volt, there is no change in current. But if you apply positive volt, the current keeps on reducing. Now, all you have to do is see what is the current change and read the corresponding voltage. You can convert the current into voltage of thunderstorm, and that is what is shown here. But so this is like Ohm's law. But unlike Ohm's law, I will call it equivalent Ohm's law, because this is not a straight line, it's a curved line. Okay. And if you're interested, I can tell you why it is curved later on. And so we get a maximum potential of 0.19 gigavolt, which is very close to what Wilson predicted. But then we got ambitious and said, okay, let's look at what is the electric field monitors telling. So you see, this is the first one, the green one, then the red and black, and then blue one. And you see the electric field first appears in the green one, and then it appears simultaneously in red and black, which are approximately 4 kilometers away, and then in the green one. So the cloud is not stationary, it's moving. It has traveled 6 kilometers in 6 minutes, which means it's traveling at a speed of 60 kilometers per hour. So now we know the linear velocity. Okay. Now, what do we do next? We said, okay, let's look in the field of view. Not in 18 minutes, every 2 minutes, because 18 minutes is an average. So first 2 minutes, first the effect appears in the easternmost directions, northeast. Then you see it grows and grows and grows. So it's basically moving, in angle with respect to the telescope. And then it appears in south, and again it develops. Now you can use each of these pictures to calculate the voltage. This voltage is much higher because now you eliminated the pixels which don't have signal. And the average comes out to be 1.3 gigavolt, which is 10 times higher than what has been ever measured. And you can see how rapidly the cloud is getting charged. So the thermal mechanism is very powerful. It took only 6 minutes. You also know the angular velocity. Now you know angular and linear velocity, you can calculate the height. It's 11.5 kilometers above sea level. And since we know the extent of this cloud in the field of view, we can estimate what is the minimum size of this cloud. We calculated the radius. You take pi r square, right? And you can get the area. So here is the summary of properties of this cloud. So electric potential, I have already mentioned. This is consistent with Wilson's prediction. It solved another very important mystery. And that is, people have been NASA satellites have been detecting what are known as terrestrial gamma ray flashes. These are gamma rays of 10, 20, 30, 40 MeV. You ask any nuclear physicist present here, can you produce 10 MeV gamma rays by radioactivity? Not possible. So these are produced by Bremsstrahlung, which is only possible if you have high energy electron, which gigavolt potential can produce if you have a discharge. Now it was moving at 60 kilometers per hour at 11.5 kilometers, which is top of the troposphere, where the jet stream lies. Total area was 400 square kilometers. The power required to sustain this thunderstorm is 2 gigawatt. The total energy stored at maximum was 720 gigajoules. So I gave this talk, that's why Nagoya is there. Whether you are in Mumbai or Nagoya, this is enough to supply power for 1 hour to the entire city. That much energy is stored. Of course, we can't harness it, that's a different matter. And this power is more than the biggest nuclear reactor, hydroelectric or thermal generator ever built by human beings. So this is was interesting. And then this is the abstract of the paper, and actually got delayed by two months because PRL decided to publish as a focus article. So the next focus articles, they have one article as the focus article of the issue. So it got delayed by 2 months. And then we didn't do anything. The physical review letters did all the publicity. So there were articles everywhere in Nature, Science, New Scientist. My favorite is National Geographic. Actually, there are more than 100 reports.
So this the calculation about 1 GB was for a particular some area or something. Have a cloud.
No. 1 GeV is voltage. The energy stored is for a given area. See, it's a charge capacitor. So all you have to do is calculate half CV square, right? You get the energy stored. Yes.
That is about 1.3.
1.3. Yes.
Prediction was about
1. Yes.
The same extension.
See, you can have a small cloud with 1 gigavolt potential, not a problem. But if you're a large cloud, then you have more energy, right? So energy and voltage are two different things. You can develop high voltage for a small cloud also. Nothing prevents you from doing that. In this case, it happens to be a large cloud, and maybe that is how we are able to see it. See, we saw 7 such events over a span of 8 years. And this is the largest of them and simplest of them, so that we could analyze it. Because normally what happens is the muon telescope looks at 2.3 steradian. The electric field monitor looks at 2 pi steradian. So you have flashes going on everywhere. And you don't know which one is flash is responsible for producing your muon intensity variation. So because we had only one flash and one muon event, we could correlate with them because it's a simple structure. Okay, now this is just a thing. Anyway, one of the things I was trying for last few years is to have a memorandum of cooperation between TIFR and Institute for Cosmic Ray Research, which is the leading institute, is part of Tokyo University. Once when Professor Ramakrishnan became director, it moved very rapidly. And last March, it was signed by Ramakrishnan and Professor Kajita, who is a Nobel laureate, on 31st March 2022. Which also happened to be the last day of his work as director of ICRR, because he decided to step down to concentrate on other things. So this was one of his last tasks to strengthen India-Japan cooperation. This is Ramki signing from TIFR end. Professor Kajita on behalf of Tokyo University, because they are like the equivalent of TIFR, right? And the two directors are very happy after having signed the memorandum of cooperation, and we hope this collaboration will thrive. Japanese are very excited about it, and some of my Japanese colleagues are there. They are watching it. They were witness to this also. So I will now quickly summarize. So this was set up by Tata Institute of Fundamental Research as a field station nearly 69 years back. Now it is home to India's largest cosmic ray experiment. Research in CRL has become multidisciplinary. As I showed you, it has not only astroparticle physics, it has atmospheric physics, solar physics, space weather, galactic and extragalactic astronomy. And recently, the Council of Management has approved that this should be upgraded into a National Cosmic Ray Center. Of course, this will take time. This is a work in progress. And I will just show a couple of pictures. So Ooty, with its near equatorial location, serves as a very unique site. Again, I don't have time to go into. That is a unique advantage India has. Development of new detector and analysis technique bode well for a bright future. And based on the successful past, this India-Japan collaboration is poised for glorious scientific discovery. That is my view. Everybody may not agree with that. Okay, so this was a funny one. Why I wanted to show you is, recently Professor Ting invited me to Geneva to spend a week with him. And I used to pride that I drive everybody around. So he invited me for lunch, and then you see he said, let's go to the lab. This was on a Sunday. He's 87 years old. So that made me feel I'm very young in comparison, He's 2 decades older than me. and he's going strong. So that was very inspirational. This is the Grapes 3 team. If somebody is missed out, blame Miran. He prepared this slide. No, it's my mistake if I have missed out. There are many, many people who have contributed. It was not done by one person. But I want to show you this one, collage. This is Dr. M.R. Srinivasan, who was the 5th chairman of Atomic Energy Commission, whom I have known from the day I joined TIFR. But he came to know me when he became chairman of Atomic Energy Commission. Why this quandary? I can explain you afterwards. He has been a great supporter of fundamental research in TIFR. He has been a great supporter of the work we do in UT. He, in fact, lives in UT. And he was instrumental in setting up of NCRA and NCBS. Under his chairmanship, NCRA, NCBS, and Homi Bhabha Center for Science Education were approved. And, I don't know to what extent it happened, but he was the man responsible. Professor B.V. Sreekantan, of course, is my mentor. And I have known him all my life till his passing away 4 years back. And this is Professor N.G.K. Menon. I came to know him only last 10 years and greatly enjoyed conversations with him. He was a frequent visitor to UT. This was during his 80th birthday. We honored him. Professor Sreekantan offered him a Toda tribal shawl and a book which is titled History of Uta Command. Before I conclude, I would like to acknowledge my wife, Nupur. She has been the rock of support for me. While I disappeared for months on end to go to UT or elsewhere, she took care of the family while working as a full-time school teacher. And she is better than me in everything except physics. So I owe a great deal of thanks to her. So thank you very much.
Many congratulations, Professor, for your wonderful lecture.
Thank you.
Thanks very much, Gupta. So, I mean, this was on sort of expected lines coming from you, and you really took us through this long journey of almost 40 plus years and mixing at ease the physics, the instrumentation, and also various, personalities that influenced your career both as a physicist or otherwise. And it was very interesting. And I'm sure a lot of anecdotes and details you must have hidden just because of lack of time. So if there are any questions, maybe, or even comments or something, both from the physical audience here and also those, I think we have a lot of people on Zoom. If any short questions, I'm sure you will be happy to answer.
Oh, yeah. My pleasure. Thank you, Satya.
Yes.
This thunderous or lightning work, was it pre-planned or it just some accident?
It was something which was never planned. And when we started seeing its effect on muon intensity, what we used to see that certain direction muon intensity is reducing, but not everywhere. So it was intriguing. In fact, the first person again to point out was, I'm not sure, either Hayashi-san or Kawakami-san, because they were looking at muon angle data. And we were intrigued, but we didn't take it seriously until this idea dawned that yes, maybe it has a great deal of significance. So it was certainly not planned, but the electric field monitor was planned, which enabled this measurement to be made. And when we submitted this paper, it elicited very hostile reaction, as you would expect, especially by so-called experts. See, we had the advantage, we didn't know anything about this field. So whatever we thought is, justified either by calculations or by what our data is telling, we went ahead and published it. But the experts said this cannot be done. Then anyway, so there were 3 referees and they had some questions, so we answered. They were satisfied. Afterwards, many people raised questions in many conferences. And sometimes they used to be hilarious. One was actually a Japanese colleague, and not from our group, our collaboration, who said, we don't see this effect. And you are claiming you are seeing it. Then, at some point I found I could no longer afford to be diplomatic. I said, you have a 4 square meter detector. We have a 560 meter square detector. You have 1 direction measurement. We have 169 direction. How can you compare? It's like this, you put in your backyard a gravitational wave detector and you say, how LIGO can detect gravitational waves when I'm not seeing in my backyard? How sun people can detect Higgs boson? I'm not seeing in my pelletron. So it was like that. So sometimes it can be hilarious, but it was interesting and fascinating. Walid.
What is the uniformity? Like how thin you can make and what will be the level of uniformity one can achieve?
Okay. See, we have tried up to 5 millimeter. In fact, I will tell you, one of the persons who asked precisely this question was MB Kurup. When we succeeded, he said, can you make, because for some positron detection, etc., he wanted a millimeter thick. See, the problem is, unlike conventional method where they use liquid and polymerize, it's much easier. What we are doing is we are taking polymer, melting it, and repolymerizing it. So their surface tension plays a part. So if you want, let's say, thin surface, then in principle, we can do it. But because of surface tension, you don't get uniform thickness. But up to 5 millimeter, no problem, with say about 10% accuracy. But if you have slightly thicker scintillator, then the non-uniformity is much, much smaller. But as you can see, because of surface tension, because even when you melt, it's like a viscous fluid. It is not a free-flowing liquid, So because of that, some undulations come. But if you are interested in small size, I think it should be possible to do it. Even a couple of millimeter should be possible. We have not tried because we didn't have a need for it, but I think it's possible to do it.
Okay. I see two, of course, you could ask some more questions. But meanwhile, I see two questions from the Zoom audience. The first one was Professor Vivek Datar. Yeah, you can go ahead.
Can you hear me?
Yes, Vivek, we can hear you.
Thank you. It is a very nice colloquium. My question relates to the voltage, the sign of the voltage. Are there cloud formations or whatever, thunder cloud formations where the voltage is the opposite of what you might have used in your model?
Right. Very good question. Very good question. Yes, there have been instances where people have seen opposite polarity, but it seems it's very, observationally, see, we don't know whether it should be or should not be, but observationally, it seems, that almost invariably you see this positive and positive top and negative bottom. Okay. But there have been cases. See, there is another factor. What happens is most of the lightning which we see is not cloud to ground. It is cloud to cloud. Okay.
Mm-hmm.
So it is a murky field in some sense. I would say we are just lucky that we saw a cloud which was unique in the sense there was no other thunderstorm activity in the neighborhood. As I mentioned in response to earlier question, that we have a field of view in the muon telescope of only 2 steradian, 2.3 steradian. The half hemisphere is 6.2 steradian. So we see only 1/3 of the sky. But lightning is happening in the entire visible sky, right? When thunderstorm or lightning activity is not confined. Depending on distance, it can be at very large angle. So it's very hard to ensure that the lightning, that only lightning should happen in that solid angle. So most of the events we see, it's very hard to analyze because of multiple lightnings combining with one observation that we make.
Okay, so can I ask you for a comment? If one would have a magnetic device there, which would be able to track mu plus and mu minus, would that help, in identifying this voltage difference, the sign of this voltage difference?
See, problem is that the thunderstorms typically have a half-life or whatever you want to call mean life of about 10 to 20 minutes. And it is very hard. In fact, you make a very good point. You see, one of the challenges because all the earlier measurements have been done mostly by balloons. So balloons are slow moving objects, right? If you launch a balloon, if it happens to be in the right place at the right time, it will measure some voltage. But it will measure local voltage. A balloon cannot measure 2 kilometers. The advantage of muons is that they are traveling at speed of light, so they can sample anything, right? So that is the advantage. So that is one difference because of which we could make this measurement, which the balloon-borne instruments cannot. In fact, after Second World War, many American groups used fighter jets for making such measurement. And in one of those attempts, the lightning struck the aircraft and it nearly crashed. After that, they stopped making the aircraft-based measurements because their belief was it's a Faraday cage, nothing will happen. But Faraday cage or no cage depends on how much discharge energy is there. You know, it doesn't offer you protection. It can bypass, but only up to some extent. Yeah. So I have a feeling that it will be very hard to measure any kind of charge or those kind of things.
No, not charge. What I meant is you measure mu plus, mu minus on the ground, like you have done on the surface, but using a device that can separate mu plus and mu minus.
Okay. So one difference is, yes, there are magnetic spectrometers people have developed, but see, typically they're small area, right? Only in accelerators like L3, for example, that instrument was used, or some other instruments which have large area, But then most of these accelerator-based spectrometers are deep underground, 40, 50, 60 meters, where you don't see GeV muons. You see 70, 60, 50 GeV muons. There you will not see any of these effects. You need to see low energy muons that we are seeing. So the main limitation is the area that is available. There's no way anybody can build a magnetic spectrometer which is 1,000 square meter. That is the challenge. A small area won't do, because then you will lose precision, because remember, we are talking of 1%, 0.5% intensity variations.
Maybe we can discuss it a little later.
Absolutely.
Yeah, we're also
Thank you.
short of time. So, Reddy, you have a question or comment?
Yeah, I have a question. Maybe a little embarrassing, but I requested my professor just to comment on this. Professor, we have a muon stations, and our ex-colleague retired last month, abruptly brought abandoned circuit from Atlas 10 years back and suddenly implemented, and the data validation is not done. And how you feel, and moreover, it is not discussed in R&D meetings under Indo-Japanese collaboration. Being a ex-founder of Grape 3 experiment, and under MOU, how you feel?
Okay.
Okay.
So,
Okay, Reddy.
Reddy, okay, I will answer this way. See, okay, you make a point, but I think it is better to discuss it within our collaboration. In this audience, I don't think it will make sense. But any question you have, any comment you have, I think it should be discussed. I believe that one should have open discussion, even if we disagree. See, I began my life here by disagreeing with my thesis advisor. And nobody ever stopped me. So I think we should follow that tradition, that we should discuss. But I think this is not the place, I would say.
Yeah, thank you, Professor.
Okay.
Thank you.
Thank you, Professor. Thank you. Thank you, Satya.
So let us thank Professor Gupta for his wonderful colloquium today, which really brought us a lot of memories, but also took us what kind of physics that can be done if you have an instrument which is designed and maintained with such kind of stability. It can do not just only physics, not only cosmic ray physics, it can do varieties of physics, and the applications could be far and wide and deep. So let us thank him again by
thank you.
This thank you very much, sir. Thank you. Thank you, Satya.
Thank you, Satya.
So please join for a cup of tea in the West Canteen. Thank you very much.
Many congratulations, Professor. Many congratulations.
Thank you, Reddy.
So good use of